So a warm welcome to you all to our first Energy Futures Lab research webinar of 2022. I hope you all had a good Christmas break, a well-earned break over the holiday season. This webinar is entitled Flow in Porous Media in the Energy Transition, and it will be headed by Martin Blunt. So for first-time attendees, the key objective for this webinar series is that it showcases the diverse energy research that takes place across Imperial College. Some very brief housekeeping: that during the presentation that you submit your questions into the chat box, and we will be able to answer them after the presentation. So today's speaker is Professor Martin Blunt. Martin is the Chair in Flow in Porous Media and has been a professor at Imperial since 1999. He was the head of Department of Earth Science and Engineering from 2006 to 2011, and he was elected to the Royal Academy of Engineering 2019. He is also the editor-in-chief of the Journal in Transport in Porous Media. Martin's research interests are in multiphase flow in porous media for applications in oil and gas recovery, geological carbon storage, contaminant transports, cleanup in polluted aquifers, and fibrous porous materials. So with that introduction, Martin, I will hand it over to you for your presentation.
Okay, well, thanks very much for the introduction. So I'll just put up my slides. Okay, so I'm going to be talking about flow in porous media in the energy transition, and it's very much aligned with the interests of the Energy Futures Lab that I've been associated with ever since it was founded. So the first part of the title is what is flow in porous media. So let's just talk about what flow in porous media is. So a porous medium is basically a solid object that has holes. We're normally only interested in if those holes connect. So you can have water, air, oil, whatever you name, in the holes, and these can flow. And flow in porous media problems are really ubiquitous, right? If you make your filter coffee in the morning, if you think about rainfall, water and nutrients moving through soil, even soaking a baby's nappy, these are all flow in porous media problems. They're always where you have a solid substrate, your coffee, your soil, the nappy, and you have a fluid moving through it. You also get the same thing in biological materials. Water uptake in plants, gas exchange in your lungs and blood are other examples. The third type of example, and one that probably is a discipline has received the most interest historically, is sedimentary rock underground is also normally porous and permeable. And that rock can contain fresh water. In fact, the main source of fresh water on the planet is not in rivers and reservoirs, but actually underground in porous rock. At depth, that water becomes salty, but it will also contain oil and gas resources and can be also used as a store for carbon dioxide or hydrogen. And of course, this is where we are heading in today's presentation. So just to give you one example of a flow in porous media problem that is clearly related to the energy transition, is at the moment we're producing large amounts of carbon dioxide, and that's damaging the climate. While it's obvious that we should become more energy efficient and move to non-carbon intensive ways of generating electricity, we are still burning fossil fuels. So one idea is to capture the CO2 that is produced from heavy industry or fossil fuel burning power plants and inject it deep underground. The same idea that you can be used for hydrogen storage. So if we produce hydrogen as part of a renewable economy, how do we store that hydrogen? And if you're doing it at large scales, the cheapest and most effective way is to do that, again, in underground permeable reservoirs. Okay, and it is fundamentally the opposite of oil and gas production. In oil and gas production, you have oil and gas deep underground and you want to produce it. In storage applications, obviously, you want to put it underground. So many of the major societal challenges for this century do involve flow in porous media, basically flow through the pore space of a rock principally, but other materials. So we talked about CO2 storage. Groundwater is a major issue. Do we have enough fresh water for drinking and agriculture? Geothermal energy, extracting heat from the Earth's surface, hydrogen storage, and as I said, oil and gas production as well. And the reason why I've sort of slightly greyed out the oil and gas production is that historically, simply because of the economic benefit of this application, is that much of the research in flow and porous media has been funded by oil companies and associated with improving oil production. And I'm going to talk a little bit, before I get into the technical details, about how we're transitioning both our teaching and research in that area. So carbon capture and storage, if you look at this diagram here, at the moment we produce somewhere between 30 and 35 gigatons of carbon each year. These are various scenarios of how much CO2 would be captured and stored underground if we're going to meet net zero. And you see by 2050, we're looking at somewhere between 5 and 30 gigatons stored each year. And that would create an industry in terms of volume of fluid injected that is large as the current oil and gas industry, if not larger. So managing the subsurface, understanding what happens underground is clearly very important. So here again, listing the challenges. So the UK Climate Change Act, probably you know this, we are committed in the UK to get essentially to net zero by 2050. That's consistent with the Paris and climate change targets. But as I said, flow and porous media has traditionally been associated with increasing oil and gas production, and clearly hitting these targets is incompatible with the current level of production and use of fossil fuels. So I'm going to say a little bit about how that's affected Imperial College, and I'll start with this picture. For those of you who can think back just before lockdown, I took this photo the day before Imperial closed in March 2020, and that's the statue of Queen Victoria in the main entrance that has been decorated. There was a climate change protest. There was a student sit-in, and that was largely associated with Imperial's links with oil companies and investment in fossil fuel companies in its endowment. There has recently been published by Imperial the Socially Responsible Investment Strategy, and I've got a quotation from there. What it means in essence is it doesn't mean that we'll no longer work with, say, oil companies, but it does mean we'll only work with those companies that have a genuine commitment to get to net zero by 2050 and on topics that are consistent with that. So we are no longer going to be doing research whose principal aim is to improve oil and gas recovery. And I hope you'll bear with me if I move sideways a little bit to say how that's impacting our teaching as well. So if you walk through the entrance of the Royal School of Mines, that's the building in which our department is housed, and you look carefully, you will notice written by the main entrance is a list of the subjects that are taught in the building, and oil technology is one of them, and we have been teaching that since 1913. And we've been explicitly teaching master's programs in petroleum geoscience, petroleum engineering since the 1970s, associated with North Sea oil production, but also with a more global remit. So, of course, the question then comes, if we're serious about the energy transition, we need to change the focus of our teaching and research away from that to be consistent with the college's public position. But the fundamental skills, I mean, basically geology, understanding what's in the subsurface, and flow and porous media as a scientific discipline, these are relevant to very important subjects related to the energy transition. And so we're going to continue to teach these fundamental skills, but with a rather broader remit. The other thing, of course, you know, we're in a data-rich, computationally advanced society this century, and that's something that we're very strong at in a department, and so we want to teach those skills to our students as well. So the picture here is a picture of Professor Alan Gringarten. He reorganised our petroleum-related teaching 25 years ago, and we're obviously having a new generation, a new look. We still do need well-trained geoscientists and engineers, but we are aligning both our teaching and research with our sustainable or socially responsible investment strategy. So we no longer teach the MSc in petroleum geoscience, which is principally associated with finding and exploiting petroleum reserves. And this is the last year of our petroleum engineering course as well. So we're going to launch a new course next year, which is called Geoenergy with Machine Learning and Data Science, which is our GEMS course. GEMS is nice acronym. So it's subsurface geoscience and engineering with a focus on the energy transition, but also teaching skills in machine learning and data science. Okay, so it basically trains our students in a way that's a little bit more fit for the next generation. Okay, and it links in with the other teaching in the department that again has a very strong computational basis. So I know this may not be terribly relevant, but if anyone's interested in the course, obviously it's an Imperial course, it's highly competitive. We're looking for students with a good sort of physical science, engineering and maths background, some coding experience, and obviously an interest in the subject. Okay, so that was a little bit of context, but I think it's an important context because the research I'm going to describe when it gets to the end has been funded largely by the oil industry, and some of that has been related to understanding oil and gas recovery, which will become evident. But what we need to understand is that flow and porous media is a scientific discipline, essentially a branch of fluid mechanics with lots of different and exciting applications, which we are now pursuing. So what actually do we do in our laboratories? So if you look here at the picture, you might recognize this. This looks like something in a hospital. It is indeed a medical CT scanner. We use X-rays to look inside rocks or other porous materials. And we can do this, you know, at the size of a person. The problem here is that the resolution is quite poor. So when we're looking at rocks, if you were to look at the Royal School of Mines, that's made out of a porous limestone. You can't actually see the holes in the rock. So you need to get down to sub-millimeter micron scale resolution. It's not a problem with X-rays because X-rays have such a short wavelength, but a medical CT scanner doesn't hack it. So what you need is what's called a MicroCT scanner, where you have an X-ray source that you place close to your sample, and then you image non-destructively in 3 dimensions. And we can look at the rock or the porous material, the solid material, and the fluids within them at micron resolution. You'll also notice that we got here something in a gold jacket. The piece of rock is between about 5 and 15 millimeters in diameter. The gold jacket means that we can impose the high temperatures and pressures that we may see deep underground for storage applications. The only problem with the scanners we have in our department is that each image takes about an hour to acquire or longer. And if we're looking at fluid movement, a displacement, obviously we're not capturing the dynamics. So we can go to a synchrotron where we have electrons that zoom round in a large circle near the speed of light, and they give off a very bright beam of X-rays. You can see here, so bright it's ionizing the air, and we can take then 3-dimensional images at micron resolution, now down to a time every second. Okay, so it is like having X-ray spectacles, but even better than that, because actually you get a 3-dimensional image. So here's just an example of what we can do, and this is an application for carbon dioxide storage. So we have a piece of rock here that's a couple of millimeters across. Okay, this is from an experiment. I know it's fancy image processing, but what you're seeing here in red, segmented, it's not really red, but just to make the image clearer, is the rock. It's a limestone, right, calcium carbonate, and what you're seeing now as these blobs are carbon dioxide trapped within the pore space of the rock. So the rest of the fluid in the pore space was water. This is carbon dioxide. The different colors are just different blobs, right? And what we're showing now is we've taken a single blob. We're looking now about 100 microns across. This is the carbon dioxide. The blue is brine, and the red is the solid rock. And one of the things we look at, because it affects basically what's happening within the pore space, is the interaction of the 2 fluids with the solid. So the yellow line is what's called the 3-phase contact line, where the 2 fluids hit the solid surface. And what we're going to do from this image is we're going to measure the contact angle, which is the angle that the fluids make with the solid. And we're going to show that the contact angle, or what we call the wettability, has a big impact on the behavior. So here, what we've seen is we've got CO2 here, we've got the rock here, we've got brine here. And what we notice is that the CO2 doesn't like the surface. The brine actually is energetically favorable to be next to the surface, so the CO2 tends to stay away from the surface. The contact angle actually traditionally is measured actually through the water phase, so this will be a contact angle of about 45 degrees. Now, why is that important? So here's an example from synchrotron imaging, so it's time resolved, and we can see the videos, actually two fancy videos here. In this case, the displaced phase is oil, not carbon dioxide. And the water, although it's transparent, you can see what it's doing, it's pushing the oil out. But because the water likes the solid surface, it's the wetting phase, it also tends to accumulate in a narrow region of the pore space here, and then surrounds a blob of the non-wetting phase. So what you're doing is you're trapping the non-wetting phase within the pore space. So in oil recovery, where we started, we know this, you know, you drill lots of wells, you spend $1 billion, you're pumping as hard as you can, and you're really lucky if you get half the oil out. Okay, and one of the principal reasons is the oil gets trapped in the pore space. In carbon dioxide storage, that's good news, because you want to inject the CO2 and you don't want it to come out again. And in fact, even if you were to drill wells and pump as hard as you can, you're going to retain most of the CO2 in the pore space. Okay, the other video is just showing it 12 round, just for visualization. So here is an example of some of our work on CO2 storage. So what's shown in blue here is after drainage, you inject CO2 into the pore space. The blue shows the carbon dioxide that's connected through the pore space. So that's a bit of a concern, because that carbon dioxide could continue to move, and maybe people say, well, it continues to move through the rock deep underground, but eventually it's going to find a way to the surface. It's going to escape. But as it moves, it doesn't leave a vacuum behind. It doesn't move as a sort of great big bubble. As it moves, it's displaced by water in the pore space. And the water, of course, tends to fill the narrow regions of the pore space, trap the carbon dioxide in the wider regions. And what's shown here in the different colours is carbon dioxide that's trapped in the pore space. And once it's trapped in the pore space, it can't move. It's not going to escape. It may slowly dissolve and react. But at the local scale, you do get secure storage. And so this is what you see here. This is the saturation that you put in and how much gets trapped. You actually trap most of the carbon dioxide. And that doesn't mean to say, oh, the rest of it's going to move and escape. No, that will move. And then as that continues to migrate, more and more will get trapped. So it's a very effective mechanism where you would trap the vast majority of the carbon dioxide as it migrates through porous rock deep underground. But so far, we've been looking at rocks. So it's very much, you know, it's an earth science department that I'm in, you know, it's very much looking at rocks underground. But it turns out that that's not the only fascinating porous media problem, and certainly not the only fascinating porous media problem that's associated with the energy transition. So here we have, for instance, an electrolyzer, okay, that's used to produce gases. So gaseous reactant, CO2 or hydrogen and oxygen reacting together to generate hydrogen. We'll talk about the reverse in a bit. So this is to generate hydrogen. And what you have is you have a porous layer where you're generating gases and you've also got water present. So you've got a porous layer, fibrous porous material, where you have two fluids, basically water and a gas, that you want to flow as readily as possible so that they can react together. If you have a lithium-ion battery, it's a slightly different problem. A lithium-ion battery has a liquid electrolyte and a solid solid scaffold. So again, it's a porous medium. What you want is when you introduce the electrolyte, you want to have full saturation. If you leave any bubbles of gas, that obviously degrades the performance of the battery, and it also means that it lasts for less time. The other example, you know, we have a huge electrochemistry group headed by Nigel Brandon as part of the Energy Futures Lab is in fuel cells. So this is the reverse of an electrolyzer. Here is where you have the gaseous reactants, hydrogen and oxygen, reacting together to form water. But of course, you're generating electricity as you're doing that. And again, what happens is that the gases move through a fibrous porous material called the gas diffusion layer. And you want the gases to be able to move in, but the water that you produce, you want it to escape. So here you're having a problem where you don't want to trap the fluids in the pore space, you want them to flow. And of course, that's exactly the same as what you might traditionally want for oil recovery, right? If you want to recover a lot of oil, you want the oil to move over a wide saturation range. And what you normally do is you get the oil out by injecting water, by pushing in water to displace the oil. So you want both the oil and water to be flowing over a wide saturation range. So when we're looking at flow in porous media from a more general perspective, you know, we're not in an application silo. Basically, there are two things we want to understand and design. One is trapping. So you want something trapped in the pore space. Okay, so we've shown that with CO2. The other example that we're all, unfortunately, all too familiar with now are surgical masks, right? A good quality mask. If you have a droplet of water with obviously potentially a virus in it, you want it either not to go into the mask at all or to be trapped within the mask. Okay, so those are examples of porous media where you want things to be trapped. The other example is actually where you want there to be flow. You've got two things flowing, normally a gas and a water, or oil and water, and you want them to flow over a wide saturation range. And those examples are fuel cells, oil recovery, actually hydrogen storage. The thing about hydrogen storage is you don't inject the hydrogen and you just want to leave it there. You want to be able to produce it as well. Okay, so hydrogen storage and CO2 storage are actually quite distinct on what you want to design. And that's all controlled by the structure of the pores and the wettability, how they interact with the fluid surface. And the revolution in flow in porous media as an academic discipline has been the ability, as I've just shown, to use X-rays to look inside the pore space at micron resolution and look at the fluids within them as well. Okay, so from a scientific perspective, this has been amazing. And of course, there is then associated with it a number of modeling techniques to understand the behavior, but I'm not going to have time today to talk about the modeling. So I'm going to focus on this trapping and flow problem. And to do that, I'm going to introduce something that seems a bit mysterious to begin with, but you know, just a little bit of a mathematical aside. So what I'm going to do is I'm going to introduce the idea of curvature. So if we got a smooth line, at any point on this curve, I can fit a circle. And that circle has a given radius, and that's the radius of curvature. And curvature itself, kappa, is the inverse of the radius of curvature. Okay, in 3 dimensions, if we have a smooth surface, there are actually 2 principal radii of curvature that are orthogonal in orthogonal directions. And why this is interesting is that when we're looking at multiphase flow, so fluids, multiple phases flowing through a porous medium, we of course have interfaces between those fluids. Okay, so those interfaces have a curvature. Now, the interesting thing is the curvature doesn't have to be the same in both directions. Actually, the curvature has sign. You might say you can't have a negative radius, but you can think of something that's apple-shaped or ball-shaped that bulges out, right, in both directions. If we have something that's pear-shaped, you know, if I cut a pear in one direction, you get a circle, so it's bulging out, but in the other direction, it's sort of like this, it goes in, doesn't it? Okay, or saddle is another example, where you have definite curvature, but they're actually of opposite sign. Now, why this is important, for those of you who know anything about fluid interfaces, there is in fact a pressure difference between the 2 phases at the interface that's related to the curvature of the interface times the interfacial tension. And that pressure is actually rather important because it tells you the pressure that is required for one phase to displace another. Okay, so the capillary pressure. And if you want flow, you might want that pressure to be as low as possible, obviously. Okay. There's another thing you can define. You've got 2 things, 2 kappas. So obviously you can define 2 independent variables from that. Is what's known as the Gaussian curvature, which is the product of the 2. And mathematically, if we want to describe the geometry of phases within a porous medium, actually we can characterize this completely using what's called these 4 Minkowski functionals. So if we know saturation, which is essentially the volume of each phase, the area of contact, so interfacial areas, the curvature, the interfacial curvatures, and the Gaussian curvature, mathematically, actually, that does provide a complete characterization of the fluid configuration. But you might say, well, I get volume because that shows how much I've got. I can see interfacial area and curvature may mean something, but this Gaussian curvature seems a bit obscure. What does it mean? Well, there is this remarkable theorem called the Gauss-Bonnet theorem that says that the integral of this Gaussian curvature over an object is 4 pi times chi, and chi is an integer. It's called the Euler characteristic, and it's essentially the number of objects minus the number of loops plus the number of holes. And what this means, sort of in even simpler terms, is that if we've got something trapped, say CO2 trapped in the pore space in lots of sort of ball-shaped objects, this Gaussian curvature is positive, right? It's got the same positive curvature in both directions because it's a ball, and then many of these trapped blobs. So this Gaussian curvature is positive, the Euler characteristic is positive. You've got lots of independent objects. If, on the other hand, you don't want things to be trapped, what you want something is to be connected across the pore space with lots of redundant loops, so that if you were to break a connection, it would still be connected. And that gives you a negative. That's related to a negative Gaussian curvature, which means you have a curvature in one direction, one way in one direction, and the opposite way in the other direction. So for trapping, you want one phase to be strongly wetting, and it's the non-wetting phase that then doesn't like the surface and gets trapped in the larger pores. And we understand that quite well. But if you want to have flow, the opposite is not switching the wettability. The opposite is, in fact, to have this negative Gaussian curvature, to have 2 curvatures that are actually equal and opposite, right? So it's a bit like comparing apples and pears, right? The interesting thing about this is, where do we see this type of behavior? And it turns out, theoretically, and indeed in practice, that you see it in materials that have a region that, for instance, likes water, is hydrophilic, and a region that repels water, that's hydrophobic. So something that, say, for instance, here would be a carbon fiber in a fuel cell, and a carbon fiber that's coated with plastic. And at the interface here, the contact angle is actually changing as I change pressure, but it's pinned in place. And the reason is that if I've got water here, it doesn't want to go across that. It's repelled from that surface. So the 3-phase contact is pinned in place. And it turns out that if you pin where the 3-phase contact is and you minimize surface energy, you end up with these so-called minimal surfaces that have these equal and opposite curvatures. So a minimal surface, by definition, has a negative Gaussian curvature because the 2 curvatures have different signs, but the total curvature is 0. So the classic example is a soap bubble. If you imagine 2 soap rings here, then there's no pressure difference across the film, right? Because it's just air on either side. So that means that the total curvature has to be 0. So it means it's curved in one direction round like this, and there's an equal and opposite curvature in the other direction. In fact, that shape is a catenoid, right? A catenary is basically like a chain, right? It's a string that the shape it assumes when it's just under gravity. And again, that's a minimization of energy problem. Okay, so that's why there's a relationship between them. You can have other shapes like a helicoid. So you see this in equilibrium when you have contacts that are pinned. The question is, so that's good for flow, so how we can engineer it. So interestingly enough, the minimal surfaces in porous media were first discovered by looking in rocks. So what happens in rocks is you've got the rock deep underground. Naturally, it's full of salty water, and then oil from source rock, essentially from the shale, migrates into the rock, and where the crude oil contacts the solid surface, it will change the wettability. Basically, it makes it oily. But there's still water present, and the pore space of the rock is very rough, and so the water is retained in that roughness. So you get a mixture of wettability. So this happens naturally. So if we have a rock that remains water wet, sometimes it does, what's shown in blue are the interfaces between the oil and water, and those interfaces are ball shaped. The curvature is positive. But if we have a piece of rock where crude oil has contacted the surfaces, we tend to get these pinned contacts, and the average curvature is very close to 0. So for oil recovery, this actually does indeed lead to favourable characteristics. So here are some examples we've done. This is a carbonate reservoir, so this is associated with oil recovery, right? So this is work a few years ago. Carbonate reservoir from the Middle East. We start off with its natural state, which is where you first discover the field. So red shows the oil, blue shows the water, and the white actually is the carbonate, calcium carbonate solid structure. I then start injecting more and more water, and you can see by the time I get to the end where I'm just injecting water, I've displaced virtually all the oil. So in fact, rather than leaving at least half the oil behind, this has been extremely favourable. And it's because of this mixed wet state. And what actually happens, and here is pictures of the brine, is that the water is in the corners of the pore space. It then fills some of the wider regions that were previously occupied by oil, but it's not well connected. So if you were to inject water to displace oil, the water is sort of held back. It doesn't flow very readily. The oil escapes. And the water only flows readily once it connects through the wider regions of the pore space. So although this is a little bit technical for a general audience, here is the capillary pressure. The capillary pressure, I said, if you have a true minimal surface, is actually 0. It's not exactly 0, but it is in fact really quite low. This is what's called the relative permeability. This is the fraction of the flow conductance taken by a phase as a function of its saturation. So if we have no water, the water doesn't flow. As I increase the water saturation, its relative permeability increases. And obviously, if I get to water saturation of 1, it will be 1 by definition. But it stays quite low. The water is held back in the pore space. The oil, on the other hand, as I increase the amount of water, there's less oil, so the oil relative permeability goes down. The oil continues to flow down to very low saturation and flows more readily than the water over a wide saturation range. So that was, some of our previous work on oil recovery. But if we're now going to move to the energy transition, and particularly if we're going to look at different types of material, what does this imply? Well, for CO2 storage, we've looked at CO2 storage both where the CO2 is water wet and where it's no longer water wet. And I don't have time to go through that because it's quite a technical discussion, but we do have ways in which we can understand and try and design the injection to be as effective as possible. When we come to other fibrous manufactured materials, there's much more opportunity for design because we can make the material in the way we wish. So just for interest, maybe, how do surgical masks work? Well, if you get a proper surgical mask, you'll notice it's actually quite plasticky, right? If you dip it in water, it actually sort of repels the water, and you think, yeah, that actually makes sense, doesn't it? So if you cough, right, or droplets of water come from you or from someone else, you don't want them to go into the mask. If you do have them in the mask, you want them to be trapped. So what you do is you make actually the fibers, they're plastic fibers. They repel water. Water is non-wetting. Water gets trapped in the larger pore spaces. But it's a little bit more subtle than that. Turns out that obviously the most dangerous thing is what's called aerosols, which are very tiny droplets that still can contain viruses that can actually fly through the pore space of the mask. And of course, you can't make the pore space smaller because then you can't breathe through the mask. So what you have to do there is you actually have to attract those little droplets to the surface. So a proper surgical mask actually has layers of material that repels water, so traps the big droplets, and material that attracts the very small droplets so they stick to the surface rather than getting to you or getting to someone else. So that's trapping. In fuel cells and electrolyzers, the idea here is you want flow. So for that, you have the mixed wet state. And in fact, empirically, that's done already. You have these carbon fibers, they have to conduct electricity, they're naturally water wet, but they get coated, partially coated is the key point, with Teflon, which makes them hydrophobic. So you get naturally a mixed wet state. And in our labs, using the same image and analysis technique, we've shown that we get almost exactly minimal surfaces in those cases. The idea is that we should do the same for electrolyzers. Okay. For lithium-ion batteries, it's a little bit different. You actually want a strongly wetting substrate so that you completely saturate the pore space. So there's lots of opportunities here to design this to maximize performance. So does it matter? The answer is flow in porous media, as I hope I've illustrated, has a very wide range of increasingly important applications. Just because we're not working so much on oil and gas doesn't mean to say there's nothing to do. In fact, there's plenty to do. And in fact, I would describe as becoming increasingly important. And furthermore, that we have new tools, particularly high resolution three-dimensional imaging, that potentially could transform the subject. So I'll finish there, and I will acknowledge the sponsors, which to date have been principally from the oil industry, even when we've been looking at CO2 storage. And I've got here plugging a book I wrote 4 or 5 years ago now, but actually much of what I've just shown here is post-dates that, right? So it's all new material. So thank you very much, and I'm happy to answer any questions.
Thanks, Martin. I believe there should be some questions on the right of the screen.
Okay, sorry, I'm looking in chat rather than question and answers.
Okay.
Okay, published. Okay, so I can see them. Yeah. So sorry, Alex, it's my fault for being a bit slow here.
No worries.
Okay, so maybe I should start with the first question, actually, not the most recent. Okay. So there's one question. Thanks for your lecture, Professor. There's one question I want to ask. We know that when we evaluate capillary pressure with the Leverett J function, we have two conditions, lab condition and reservoir condition. So yes, so one of the things here, maybe for the more general audience, is that you can measure the interfacial properties, but obviously it's more convenient to measure it sort of, I would say, at lab conditions, right? So atmospheric pressure and ambient temperature. But actually, when we're looking at subsurface storage or recovery processes, we're at high temperatures and pressures. Okay, so we need to correct for that. One of the things we can do in our laboratories is that we can, even in these small samples, when we do the imaging experiments, we can impose high pressures and temperatures. So in fact, we can do those measurements at reservoir conditions. And when I showed you the pictures of CO2 trapping in the pore space, those were done at high temperature and pressure conditions. You had supercritical CO2. When I showed the oil recovery applications as well, those were typical reservoir conditions. I have another question here. That's from you. Okay, so good flow is obviously good for getting the CO2 into the subsurface. It's going to be an aquifer rather than depleted oil and gas field. Is there a challenge about leakage? Yeah, I think the point here is that one of the principal public concerns about CO2 storage, and indeed could be hydrogen storage as well, is that the gas will leak. Okay, so that's one of the reasons why we're doing our research. What we're showing is that as the gas migrates through the pore space, a significant fraction of it gets trapped. So the idea that there will be a catastrophic leakage of the majority of what's stored is really, virtually implausible. The major concern actually about leakage to the surface is normally associated with pressurizing the subsurface. So when you inject something, the pressure goes up. Okay, and the concern is that that may activate faults, so you get small, detectable seismic activity, mini earthquakes. But that's also associated with allowing flow paths to develop in the subsurface, or indeed there's leakage through existing wells. So these are things you need to carefully select your site. You need to monitor your pressure to ensure that these things don't happen. And of course, monitoring potential leaks. But my view is that, yes, that it is possible with good engineering to ensure that there's really minimal leakage from these sites. I don't know if you wanted to ask a bit more about that.
I guess in terms of providing this information to the public, what is the best outreach that the scientific community could give in places, for example, Germany, that have quite a negative opinion on CCS?
Yeah, I think what we do is, in fact, we do we have a large group that works on carbon capture and storage in Imperial College, and we are involved in, say, the Science Festival, and we are thinking about other types of outreach. I think explaining the science is important. We're quite used to being, there are parts of the world where underneath our feet are hydrocarbon resources. We also pipe methane, right, everywhere, and people view this as being routine, and yet methane is frankly a more dangerous gas than CO2. So just to reassure people that this doesn't mean to say that something tragic is likely to happen. In a UK perspective, we're very fortunate because most CO2 storage sites are likely to be offshore. So there's not this nervousness that there's CO2 beneath my feet and something, bad is going to happen, or my property value is going to collapse or something like that. Okay, so I think in the UK, and indeed with new projects that have been announced, we have the opportunity to be a leader in this technology. But yeah, it does require a lot of engagement with the public, going through their concerns to assure people that we have routinely for many decades exploited gas resources, but also stored gas underground. And there are, in routine oil field operations, normally natural gas or even oil can be produced with carbon dioxide. And traditionally what we do is we separate out the carbon dioxide and release it to the atmosphere. But there are cases, nothing to do with climate change, where the carbon dioxide is mixed with H2S, and H2S is very toxic. And so what do? You inject it back underground. So there are hundreds of sites in North America where this is done, and it's completely below the radar. It's just normal oil field operations, nothing to look at here. But when we start doing it for climate change, then people sort of, want to say, get quite excited about it, what's going on. I think the other reason why there is some public hostility to CCS is actually from an environmental perspective, is saying, well, we just shouldn't be burning fossil fuels in the first place, right? Why we do this elaborate thing to store the CO2, but I just don't like the fact that we're burning fossil fuels. And the point there is that that's frankly a bit of an emotional argument. The reality is, at the moment, our world's economy does rely on fossil fuels, like it or not, and it's inevitable that we're going to continue to need to use them for the coming decades. And so if we want to deal with climate change seriously, address the problem head on and to deal with some difficult facts, then we do have, at a very large scale, to collect and store the CO2.
Thank you. I believe there's one further question as well. So one basic question: what is the difference between flow and transport in porous media?
Okay, good question. Yeah, I'm a little bit loose with my wording, certainly in a talk. So flow is just related, technically, is just the volume of fluid flowing. So you have, for instance, the Darcy flux or the Darcy flow from Darcy's law, which is the volume of fluid that flows per unit area per unit time. So it's just a sort of bulk movement. Transport, technically, is actually how, say, an individual particle would move. And the reason why that's different is if you imagine something dissolved in water, that, say, a salt or a contaminant or a tracer, will not only move with the bulk flow, but of course there's also diffusion. So there's Fick's law, right? So on average, there'll be a movement with a concentration gradient. There may also be reactive processes. It may also sorb to the rock. Okay, so when we talk about transport, that's much more general. because it's looking at the movement of individual, say at the individual molecule level, and that will include, you know, diffusion, absorption and reaction as well. So that's the difference. Flow is sort of the bulk movement, and when we're talking about CO2 injection or oil recovery, we normally talk about flow. But when we're looking at contaminant transport, if we're looking at cleaning up groundwater, for instance, it's very much a transport problem, because we need to understand the transport of pollutants.
And there's one further question as well.
Yeah. Okay, so will they reduce over time? That I'm not an expert on. So there've been, you know, conflicting views on this. My expertise is really on the storage side. The storage side is not the most costly part of this process. Actually, it turns out carbon capture and storage is the capture technology. At the moment, there is capture technology that's been around since the 1930s, but it's not as efficient as it could be. So the real breakthrough scientifically, and certainly in terms of energy efficiency and cost, would be on the capture side. And there are many of my colleagues at Imperial College and associated with the Energy Futures Lab are working on improving the capture side. So there's also associated with this, there seem to be very few providers of storage sites today that can truly guarantee very high level of capture. Yeah, I mean, this is one of the problems, is that you also, if you're truly getting down to net zero, you need to have at least a 90% capture rate. That's not just under ideal operating conditions, that's sort of, you know, the whole time. So I agree that is difficult, and as I said, many of my colleagues, in chemical engineering are working on the design both of improved capture technology, but also how you design a plant so that you would guarantee 90% capture rates. In terms of the storage, that's less of an issue. The potential for leakage from these storage sites is very low, and so, you know, they're well, you know, in most sites there will be negligible leakage, so that's not the concern.
Okay, I can see no further questions, so I think we'll call it a day there. Thank you very much, Martin, for that very interesting talk.
No, it's been my pleasure. No, and I hope that's helped people see the scene. There has definitely been a shift, you know, in our perspective on research and teaching. But it's very exciting times. Absolutely.
So with that in mind, thank you all for attending and for Martin's discussion again. So next week we'll be hearing from Dr. Ala Al-Qadahi, who will be discussing outlooks, explorations and normative scenarios, approaches to global energy futures compared. So with that, I thank you all for your attendance, and Martin again, and I wish you a good Thursday and the end of the week. Thanks very much.
Bye.
Cheers then. Bye-bye.